Hello, ladies and gentlemen, again. This is Lecture 9, which is a continuation of Section 3.2, as well as the beginning of Section 3.3. So let me get started. So I thought I would discuss something called the Monty Hall problem today, which is something that is rather surprising, at least to me. So what's the Monty Hall problem? So there was a game show that I don't know when it went off the air, but it was a television game show, and it went like this. There are three doors on the stage: door 1, door 2, and door 3. And the basic version of the game went like this. Behind two doors are goats, and behind another door, the other door, the last door, behind one door, I should say, is a brand new car. And your object is to win the new car. So you select the door. You're allowed to select any door. Let's say door number 1. And the door does not open because the game show host, whose name was Monty Hall, goes to you and says, aha. He doesn't open up your door. He opens up another door. Say door number 3, and displays a goat. So the question is, and then he says, do you want to keep your choice of door number 1, or do you want to switch to door number 2? He gives you the option of changing your decision after showing you door number 3. So the question is, does it pay to switch to door number 2? Do you increase your odds of winning? Now you might say, probably not, right? But we're going to see that there is actually always an advantage in switching. So I'm going to solve this problem in 2 ways. And you'll see one way is just by writing out all the cases that can occur. And the other case, we're going to use conditional probability to see what's going on. Okay, so I'm going to save the screen and then erase the whiteboard. Okay, so let's solve give the solution using something called a tree diagram. So this will be solution number 1. Okay, so the idea is I pick, let's just map out all the cases. I pick door number 1. Now, a lot of things can happen now. So this is my choice, right? That's my door. Now, what happens? The car location can be behind any of the doors. So car location. So it could be behind door number 1 or door number 2 or door number 3. And let's say that they're randomly, the car location is random. So there's 1/3 of a chance that the car could be behind any of the doors. Now, so that's the car location. Now, what happens? The host opens a door. Now, if the host opens cannot open up door number 1, but he can that's Monty can open up number 2 or number 3 based on the car location. right? So the probability of opening up either door is going to be a half, right? Uh, so because there are only two options there, right? Now suppose I pick door number one, and by the way, the host can open either door number two or number three because the car is located behind door number one. Now suppose I pick door number one, but the car is actually behind door number two. Then the host can open only one door. He can only open door number three because he can't open door number one. I already picked that door. And he can't open door number two because the car is behind that door. So he has to show me a goat, remember. Okay, so now, and in the last case, if I pick door number one and the car is actually located behind door number three, the host is going to show me door number two. Okay, so now we can figure out the probability of each case by going down the tree branches. You see, if the probability is 1/3, that if I pick option one, in the first case, if the car is in location door number one and the host opens door number two with probability of half, the probabilities are going to multiply in that case because the sample space here is going to be given by these choices. Choice one, this branch, and then this branch. So the probability of any given set of outcomes is going to be given a 1/3 times 1/2, which is 1/6. And in the second case, 1/6. In the second case, I should have said the probability is going to be 1 that the host opens door number three, given that the car is behind door number two. And lastly, if the car is located behind door number three, the probability is 1 that the host will open door number two. So in the next case, where it's going to be 1/3 times 1, which is a probability of 1/3. And then lastly, it's going to be a probability of 1/3 in the final case of going down from this last branch here to here and then here to here. Okay, so that's that so far. And now we're going to map out the possible cases that can occur if I switch. If I switch, what's the probability? And what about what if I stick? Okay, so what if I stay? So let me put stay here and stay here, and let me put switch over here. Oops. Okay, so now when do I win or not? Okay, so in the first case where I go, let me indicate this my magic wand. If I go along this path, what happens is if I stay, I win, right? Because I picked door number one and the car is located in door number one, so I win. If I switch, I lose. Okay, so then another possibility is I go along this branch and then this branch. If I stay, I win again, and if I switch, I lose. So same situation there. Okay, and then in the third instance, if I go along this set of branches, I pick door number one, but the car is in location number two. I'm going to lose if I stick, and I'm going to win if I switch. And lastly, it's also a lose then win situation in the last case. So that's this case here. Okay, so so what's the probability of winning? The probability of winning if I stay is going to be, let me just write it out in words. If I stay, the probability of winning, what is it? Is what? Is there are two cases in which I win when I stay, each of probability 1/6. These are mutually exclusive events. So it's 1/6 plus 1/6, which is 2/6, which is 1/3. So if I do nothing and just stick with my initial choice, it's a probability of 1/3. Now suppose I switch. If I switch, I win. If I switch doors, well, that's either you can think of that as the complementary situation, or you can take these two cases here. Each has a probability of 1/3, so it's going to be 2/3. So it always pays. It pays to switch. Now that seems kind of unbelievable, right? I mean, if you think about it, but you can actually play a version of this game at home. Take three different cards out of a deck of cards. Say, let two of the cards be have a value of 2, and let one of the cards be an ace. Put them face down. That's like the doors. And then you have a person who's the host, and you select a card without turning it over. And your host shows you another card that's like the host showing you another door and shows you that other card is not the ace. And then you decide to either stay all the time and then do this a lot of times, play this game a lot of times, maybe 100 times, and you'll see that approximately 1 out of 3 times you will win the game. And if you switch, though, if that's your strategy always to switch, you're about 2/3 of the time you're going to win. So that is one version of this problem. I'm going to actually now give you a different solution. Okay. Okay, so solution number 2 that I'm proposing to the Monty Hall problem goes like this. There are two possible cases. So if I use strategy 1, which means I don't switch, what's going on? Well, in some sense, the way you can think about it is just ignore what you're ignoring. You're ignoring Monty's new information about the goat behind door 3. So in other words, you could just pretend Monty didn't tell you anything. And then, there are 3 doors. So the sample space in that case would be 1, 2, 3. And choosing a door, whether it wins or not, the probability of number 1 is of course 1/3, 1 out of 3. So that's if you don't switch. Now, what if you switch? Well, that's the of course that what if you switch? So strategy 2. Okay, so that's switching. How can we formulate this in conditional probability language? Well, in this case, the sample space is a little different. I'm going to write it like this: 1, 2, comma, 1, 3, 2, 1, 2, 3, 2, 1. Oops, sorry, not 2, 1, 3, 1. 3, 2. Okay, what do these numbers mean? Well, let me give you an example. 2, 1 means I chose door number 1, door number 2, I should say, and the host, Monty, shows the goat shows the goat behind door number 1. So likewise, 3, 2 refers to I choose door number 3, but Monty displays door number 2 as having the goat behind it. No other cases can occur. For example, 1, 1 won't occur because 1, 1 would mean I chose door number 1, and then Monty would be showing me door number 1. That's not allowed to happen. So these are all the cases in the sample space. Okay, so now let's assume. So, for example, the car is actually behind number 1. Number 1 would be a winner. Okay, and so then uh, Monty shows number 2. So in other words, this is 1, 2, right? Okay. So so if I s- so now what are the possible ways uh, I can win, right? The possible way. Well, first of all, what are the possible conditions, right? If the door is behind number 1, so if Monty shows door number 2, then we can consider the only events which matter in the sample space are events 1, 3, 2, 1, and 3, 1. And that's because the other events, the remaining events, 2, 3, and 3, 2, are not possible. Right? Why is 2, 3 not possible, for example? 2, 3 is not possible because I chose door number 1. I chose door number 1, not door number 2, nor door number 3, right? I'm sorry, I didn't choose it. Sorry, I retract that. We're assuming the car is behind number 1, and Monty shows door number 2. But if Monty shows door number 2, that means I could not have selected door number 2. Uh, I can't select door number 2 if he shows me door number 2. Likewise, 3, 2 is not possible. Why is that? Because if I select door number 3 and the car uh, and and Monty shows me door number 2, that can't happen because I'm assuming Monty has showed me door number 2. So the only the subset of events which can only happen under in this scenario is 1, 3, 2, 1, and 3, 1. And now when do I win in this scenario? I win if the following situation occurs: 2, 1, or 3, 1 occurs, right? Why is that? Because the car is behind number 1, and I have to switch to 1 in order to win, and that's the second term here in each one of these outcomes. All right, so therefore, what are we trying to compute? The probability of A occurring given that B has occurred. And that's the same as the probability of A intersect B over the probability of B. Now A intersect B is just the same as A because A is a subset of B. and that has size 2, and the probability of B has size 3. It's 2/3. So that's where the 2/3 comes from the point of view of conditional probability. If you switch, okay. Okay, so we now come to section 3.3, which is called Bayes' formula. It's easy enough to explain this as a formula. It's usually complicated for us to think about how it's used in real world cases. So the situation I want to draw your attention to is we have two events, E and F, and they overlap in some shaded region like that. So we have events E and F. Okay, and I want you to notice that E is equal to E intersect with the sample space. And that's the same thing as E intersect F union F complement. And that's the same thing because F and F complement are disjoint or mutually exclusive, EF union EF complement. Okay, so therefore E is EF union EF complement. So the probability of E is the same thing as the probability of EF. Notice that EF and EF complement are disjoint. So we get the probabilities add. Okay, and therefore we get this expression here. Now we use the multiplication law to write this as the probability of F times the probability of E conditioned to F plus the probability of F complement times the probability of E conditioned to F complement. Okay, and we can rewrite this as follows. Finally, the probability of E is the probability of F times the probability of E conditioned to F plus 1 minus the probability of F times the probability of E conditioned to F complement. Okay, so that's Bayes' formula. I'm going to circle it. We're going to use it in the following problem. Okay, so that's Bayes. It's actually, the name was Bayes, so the apostrophe goes after the S, in fact. Okay, so that's Bayes' formula in its simplest description. Okay, so I'm just going to do one problem now in this lecture, and then we will do more problems in the next lecture. So let me clear the screen. Okay, so here's a problem connected with Bayes' formula. 0.5% of the population. So remember, 0.5% is 0.005 of population has a certain virus. So as you're probably well aware of, we have developed tests for various kinds of viruses, including COVID-19. So a test is developed. So now whenever you develop a test, there's a possibility that when you test someone who doesn't have the virus, in fact, you're going to get a false positive. That means you test positive. So in this example, the probability of a false positive is known to be, for whatever reason, 0.03. Okay, so that's the notion of a false positive. Um, and the probability of a false negative is known to be, for this test, 0.02. Okay, so let's Joe be a random member of the population, and let's call him J. And what's the probability? It's the question is, there are two questions to be asked. What's the probability that Joe tests positive? That's the first question I want to ask. And then the second question I want to ask, suppose Joe tests positive, what's the probability he actually has the virus? Okay, so I'm going to formulate it in the following way. So these are the two questions that we want to answer. So I'm going to set it up as follows. Let V be the event that Joe has the virus, and let T be the event that Joe, who's a random person, tests positive. Okay. So, right. Okay, so I'm going to save the screen and continue. Okay, so I've written at the top of the screen the information that we already have been given in this problem, and we want to know the probability that Joe tests positive. So in part A. Okay, so how do we do that? Now I want to try to unravel what a false positive means and what a false negative means. Okay. Okay, let's start off with false negative. So a false negative means you have the virus, but the test doesn't tell you you have the virus. The test thinks you don't have the virus. So if you have the virus, the condition would be V, you have the virus, and the test doesn't come out positive, the test comes out negative. So this would be the probability of this occurring is T, the complement of T uh, subject to V being true. So that would be 0.02 according to this. Okay, so now what's a false positive? I don't have the virus, so the complement of V holds, but I'm testing positive. So given that I don't have the virus, I'm testing positive, that's this conditional probability, and that's 0.03. Okay, so now I want to compute, what do I want? The probability I want to compute in part A, the probability of testing positive, right? So a probability of T occurring. So now I'm going to apply in part A the following. So what is the probability of T occurring? Well, according to Bayes' formula, the probability of t is the probability of t conditioned to v times the probability of v plus the probability of t conditioned to v complement times the probability of v complement. Okay, so what is the probability of t conditioned to v? Well, we had a formula in the previous lecture that said that p of t complement conditioned to v is 1 minus the probability of t conditioned to v. So in other words, these are complementary probabilities. So this would be 0.98 because if we add 0.02 to it, 0.02 to it, we get a value of 1. Okay, so now as far as the probability of V goes, that's the probability of a person in the population having the virus, and we were told that 0.5% of the population has the virus, so that would be 0.005. Okay, now we're already computed the probability of T conditioned to V complement. That would be a false positive, remember? That would be 0.03. And the probability of V complement is 1 minus the probability of V, so that would be 0.995. So the answer to part A of this problem, if you do the arithmetic, is 0.03475. So that's about 35% of the time. If that Joe will test positive, okay, so about 35% of the time he will test positive. Okay, so now let me save the screen. So in part B, we're asked a specific question. So we want to know so we want to suppose Joe tests positive. And then what's the probability, given that Joe tests positive, that he has the virus? So you can see this is a very relevant question in today's world. Okay, so what does that mean? So Joe tests positive means the condition T holds, and we want to know whether he has the virus, so we're trying to compute the probability of V conditioned to T. Now, by the definition of conditional probability, that's the probability of V intersect T over the probability of T. Okay, now here's the trick. In the last problem in part A, the denominator was actually computed. We saw that P of T was 0.03475. Oh, by the way, I really screwed that up. It wasn't 35%, it was 3.5%. So in part A, the answer was, I really misspoke. It's 3.5% approximately have the time he tests the virus will be positive when he gets the test. Ooh, I'm an airhead today. Okay, so what about, so let's go back to part B. So the denominator we know. What about the numerator? Well, the probability of V intersect T, we can use the multiplication law on that in the opposite way. That's the probability of T conditioned to V divided by the probability of times the probability of V, sorry. Okay, so now what do we know about that? We know from what we did already that that is 0.98 probability of T conditioned to V is 0.98 because that was done over here. We computed it, times the probability of having the virus, which is 0.005. So we can go back and now compute what we want to. It's 0.98 times 0.005 divided by 0.03475, and that gives us a value of 0.141. So the answer to the question is, if he tests positive, what's the probability he has the virus, is about 14% of the time, which is not very high, by the way. So the test is a very crude measurement of actually having the virus, even though it seems with the numbers given that have the probability of having uh, a false positive is very low. That's the false positive right here, 0.03. It's still, the test doesn't seem to really tell you when you have the virus very often, right? Only about 14% of the time. Okay, so I'm going to stop mumbling now. I saved the screen, and I'm going to wish you a good day, and we will continue with applications of Bayes' formula next time. Cheers.